Welcome to today's seminar. We are in first seminar of the fiscal year. Our speaker is Chris Cox, who is visiting us from Carnegie Mellon. He got master's degree here. He is our frequent speaker, and he will be speaking about inverting the Turan problem, which is joint work with Joe Briggs.
Yeah, sounds great. Thanks, Bernard. Right, so today I want to talk about flipping Turan on its head. Unfortunately, I don't have slides here, but I just put a slide of an upside-down Turan. But before we can get into definitions, we need, well, definitions, which hopefully everyone's seen. But let's just make sure. So if I give you H, a family of graphs, and G a graph, well then G is H-free. If G doesn't have a copy of any H in H. And of course, when H just consists of a single graph, we'll just use that single graph to do everything. Secondly, we have the Turan problem, or the extremal number, which the extremal number of H and G, this is just the max number of edges in an H-free subgraph of G. Great. And of course, throughout this talk, most of the time we'll have two uniform graphs, but all of these definitions make perfect sense for hypergraphs and even multigraphs, and we'll get into that in a little bit. So this extremal number, or Turan number, really had its start with Turan and mathcal. So the original Turan problem is determining the extremal number inside of a clique of H. So just how many edges can an n-vertex graph have that has no copy of H? And in this line, well, the first result was really due to mathcal, who was able to determine exactly how many edges you can have in a triangle-free graph, which turns out to be exactly n squared over 4. Turan later came along and determined it for any clique. And I'm not going to worry too much about exacts and lower order terms, so let's just say it's asymptotic to 1 minus 1 over t minus 1, n squared over 2, as n goes to infinity. After that, actually, Erdős and Stone were able to almost completely answer this question by showing that the extremal number of Kn with any graph H is going to be asymptotic to 1 minus 1 over chi of H, chromatic number of H minus 1, n squared over 2. There's only one case where this is fairly unsatisfactory, and that's the bipartite case, right? All this tells you is that if H is bipartite, then the extremal number is little o of n squared. Really doesn't tell you much, and we still have no idea what happens here in most cases. It's a very open area of research. However, one thing that almost becomes more natural is when considering a bipartite graph, a clique, maybe that's not the best thing to consider as the host graph. Almost more natural would be, say, a complete bipartite graph. And this actually has a name, and I can never remember how to spell this name. It's called the Zerenkowitz problem, or Zerenkowitz problem. I have no idea.
I say Zerenkevich.
Zerenkevich, okay. Sure. And this is exactly what is the extremal number of H when the host graph is the complete bipartite graph. And actually in these lines, the thing that I really want to point out is that Kavary, Soch, and Turan we're able to determine that the largest bipartite graph on 2 n vertices without a C4 is exactly n to the 3/2. We even know the lower order terms for certain values of n. And this was actually known well before we were able to determine the Turan number for C4. Incidence graphs are easier than polarity graphs, it turns out. So in some sense, this is a more natural question. Actually, let's just keep it over here. But I also want to mention a few other things that extremal numbers show up in, which, honestly, I never think of them in this way, but it's nice to note. They actually show up as just graph parameters in general. Well, what do I mean by this? Well, the graphic matroid rank, for instance, well, this is just the extremal number of G versus the class of all cycles. The graphic matroid rank is just the size of the largest spanning forest, which is exactly the extremal number of G versus cycles. Other things, well, what about max cut? Max cut, well, we can write this as the extremal number of G versus the class of all odd cycles. Same thing. Largest cut is the largest bipartite subgraph. Okay, what about the max star packing? Well, the max star packing, well, this is the largest set avoiding two graphs, right? Namely, we can't have a triangle, and we can't have a path on three edges. So this is one thing, a bit controversial, and I honestly don't like it. My co-author does. P sub t is path on t edges. I will keep reminding you. Yes?
Do you call star packings galaxies?
I like it, but no.
Constellations.
I like that. We should. And the last thing I'll mention is max star plus triangle packing. This is just the extremal number of G versus the path on three edges. Love that triangle. Yeah, Bernard cringes every time I write this. I understand your pain.
We will blame Joe for
Yes,
this.
no, please do. It's completely his fault. All right, so what I really want to ask here is the extremal numbers come up in all these things. Maybe for C4, the most natural host graph to have here is the complete bipartite graph. I mean, definitely for a clique, it seems the most natural host graph to consider is the clique. But we also have all of these other things where we can consider these as just parameters of the host graph. And, well, because I do extremal combinatorics, I like to optimize things. I like to prove inequalities. So the question that we really want to ask is, what host graph is best for a given family of graphs H? So what do we mean by best? There are lots of ways we could define this, but it certainly suggests optimizing some sort of monotone graph parameter with respect to the extremal number. Well, one of the easiest things is the edge count. That's exactly what we do. So I'm going to write this up here, and this will stay the entire time, because it's a definition that still, I don't always get right sometimes. So, EK of H, this is the max number of edges in a host graph such that the extremal number of G versus H is strictly less than K. Now what does this mean in words? This is the most edges in a host graph such that any K edges of G contain some H. Okay. So you should think that this might be a bit of a difficult problem. The more edges I have, the easier it should be to avoid some fixed H, right? I mean, my edges are more spread out, H might be a triangle, say. It should be easier to build a triangle-free graph. So let's just warm up just so we understand this parameter. It's a bit convoluted. All right, so let's do a warm-up. All right, let's first try to figure out EK of, let's say, a matching on T edges. Let's assume that K is at least T here, so we can have a matching. What should this number be? Well, we could say maybe take the host graph to be a clique, right? In which case we need to find T disjoint edges. Bernard should know something about this, I believe. You like your forest Turan numbers.
Don't you want?
But is that right?
Wouldn't you want a bunch of cliques of odd order or something like this?
Maybe. Right, but there are lots of possibilities. We don't have to restrict ourselves to the clique as the host graph, right? The host graph, it's kind of hard to, if the clique is there, I could take a giant star, right? I only get one matching edge. Might not be the best thing to do. In fact, it's very much not. The answer here is infinity. I lied to you. This should be a supremum. Why is this infinity? Well, what I could do is just take an arbitrarily large matching. As many edges as I want. So it has, for all intents and purposes, infinitely many edges. But what happens if I pick any t edges? I get a matching. Does this make sense? All right, so this answer should be infinity for a matching. All right, one more. Well, we'll do a couple more. All right, what about a star? Now that we've seen how this works. What if I want a star? Again, k is at least t, so we can at least get it. What should this answer be? Any k edges has to give me a star on t. Yeah.
Also should be infinite.
Also should be infinity. And what's the construction, Ryan?
A large star.
A large star. Again, any t edges I pick gives me a star, so certainly if t is at least k, I get a star on k edges. Okay, so yeah, this really should be a soup. All right, let's do another couple. What about ek of, let's say, so script C is the class of all cycles. I want any k edges you give me to contain a cycle. Well, what's one graph that has this? Any k edges I give you has a cycle. Any graph on k vertices, right? Particularly with the clique. Right? If I give you a clique on k vertices, any k edges I give you must have a cycle. Can you do better? Not. The best thing you can do is a clique. And very simple proof, but let's just do a simplified version. Let's first assume that G is connected. Well, if the extremal number of G versus the class of cycles is strictly less than K, well then the largest spanning tree, well, we know that this is the number of vertices minus 1, but this has to be at most K. Sorry, at most K minus 1, sorry. Right, if I don't have it, doesn't have a cycle, so I can have at most K minus 1 edges, which tells me the number of vertices is at most K, which then just tells me the number of edges is at most K choose 2. And the only graph that's going to achieve this is the clique. This is if G is connected. What happens if G is not connected? You could do a bit of hand waving, but actually we'll get into a way a little bit later where you don't have to do any sort of calculations at all to actually get the case when G is connected. Okay, let's do one more example to finish off our little warm-up, and then we'll get into some results and talking about more things. What about EK of a triangle? And all I care about, let's just say asymptotically here. I'm not going to care about lower order terms. Well, we have an easy construction, right? So if I give you a clique, right, the number of edges of Kn, this is going to be roughly n squared over 2. And the extremal number in Kn of a triangle is going to be n squared over 4. So if we kind of set this equal to k, again, we're doing some hand waving, brushing lower order terms under the rug, well then this would tell us that the clique on the right number of vertices gives us a construction which is going to have asymptotically 2k edges. Right, so n squared over 4 is k, number of edges will be 2k. Again, asymptotically.
Square root?
No.
Am I missing something?
Sorry. N squared over 4 is equal to k,
Right.
asymptotically.
Yeah. Oh,
And the number of edges is n squared over 2,
right.
just a factor of 2 off.
Okay.
Okay, so at least asymptotically we can do at least 2k edges. Can we do better? No. Why? Well, probably something you learned in a first year class. If I take a random bipartition, so if I give you G on m edges, a random bipartition has how many edges?
About half of the original.
Yeah. Has at least m over 2 edges. but this doesn't have a triangle. So I know that m over 2 has to be less than k.
Well, technically, there exists a bipartition such that there
whatever,
is.
Ryan, whatever, Ryan.
Otherwise, you got a little low.
Yeah. But we only care, at least we're doing things asymptotically. But this will tell you that m needs to be less than 2k. Or at least I can find one of this. Just telling you how to as well. So this actually tells us that ek of a triangle is actually asymptotically 2k. These parameters start making sense. All right. So there's one thing that you should notice here is that really the extremal host graph here should be a clique, right? Prove that the extremal one here is a clique. These two look a bit weird. They're actually the odd men out. You might be afraid that lots of these will be infinity. It's only the star and the matching. And I'll prove that to you. Okay. So I just want to mention a few results just to cover my bases, especially with what I mentioned earlier. We kind of already covered graphic matroid rank. What about like star and triangle packings and that? Well, let me just give you a few of our theorems, which gives you a bit of the flavor. All right, so where's the good piece of junk there? So ek of k3 and p3. So if I ask about this, I'm trying to say that I have no star packing that uses k edges, right? The largest star packing I have has at most k minus 1 edges. We can determine this answer exactly to be k plus 1 choose 2 minus the ceiling of k plus 1 over 2. And the unique extremal graphs are the complements of near perfect matchings. Just based on divisibility. Maybe I will have to have a path on 2 edges inside as well. In k plus 1 purposes. So it turns out this is an exact answer, and we know exactly what the extremal graphs are. Another one, ek of just p3. So now I'm allowing you stars and triangle packings, but you can't have more than k edges that belongs to one of these. This turns out again to be exactly k choose 2, like cycles. And the extremal graphs are either kk if 3 does not divide k, there's actually a bit of a divisibility problem here, or one host graph that works all the time, and this is a complete classification, is kk minus 1 with pendants at every vertex. So this again has k choose 2 edges, but this graph will work for any k. And these are the only 2 extremal graphs that there are here. Any k edges I pick is forced to give me a path on 3 edges, and they have the most edges possible. Last one, which maybe isn't as interesting, but I kind of like it, is a path on 1 edge union a path on 2 edges. So this graph right here. A couple reasons we like this graph. First, it's one of the easiest disconnected graphs that's not trivial. And secondly, it actually has the largest finite value of ek possible. This isn't too hard to show, but I won't prove it. It has one of 2 options, either k squared minus k, and this is for k odd, or k squared minus 3/2 k. This is for k even, and I've run out of a bit of space. But k odd, the unique extremal graph, is 2 copies of a clique of size k. And for k even, you basically take a large power of a cycle and add in a near matching. It's not too bad, but this actually has nice ties to the Erdős-Rado sunflower lemma as well, which we'll get into in just a little bit. So these are just a few examples. What's one thing you can ask? Except for these 2 silly cases, and we kind of understand why they're silly in some sense. Essentially, every single answer was the best thing to do is take a clique. I mean, this one, okay, maybe not quite a clique. P2 union P1, also not exactly a clique, but basically, is it always best to take a clique? And this was kind of the original motivation, right? Sometimes we might want a bipartite graph. can you think of a class of graphs, I mean it can be a family, that really are good for bipartite graphs, say? Just to try to, make our lives, make our problem come out how we want it to. What about the class of even cycles? Okay, well let's just see here. If I give you k and n, and I look at the class of even cycles, what's the extremal number? Well, I can have a spanning tree, right? That doesn't have any cycle. If I give you one other edge, it has to have a cycle, and it's bipartite. That cycle has to be even. This is 2n minus 1. Whereas, if I look at k, and I'm going to normalize things here, so now these two have the same number of edges, just to compare them. The best thing you can do in a clique is actually kind of take like a friendship graph, right? Take a bunch of triangles joined at one vertex. That'll have lots of cycles, but it won't have any even cycle. And that'll have roughly, I wrote this down, 3 over square root of 2 and edges. Again, about 3/2 of the number of vertices. Well, note that this is bigger than that. So at least by our very rough hand waviness, at least a bipartite graph is better than a clique for this family of graphs. Same number of edges, but one has a much smaller extremal number with the class of even cycles. And it turns out that this is correct. Theorem ek of the class of even cycles is exactly floor k squared over 4, and the unique extremal graph is the balanced complete bipartite graph. So k over 2 rounded up, k over 2 rounded down, except k equals 5. When k equals 5, you could also take the clique on 4 vertices, and that just happens to work. Silly small numbers. Okay, one thing I want to mention about this proof is this was one of our first questions, and we said, of course, it's obvious, duh. And we wrote down a fake proof. That proof doesn't work, and now it takes about 3 pages to prove this result, which surprised me. I think this should be a really easy proof. I don't know how to do it. We have to use Mantel's theorem in multiple guises. And challenge for you. I don't even care about the uniqueness. I don't care about the exact answer. Just asymptotically prove that you can't do better than k squared over 4, like in a short proof. I don't know how to do it, but I would love to see it. Okay. So these are just a few results we have in graphs. So actually, let's leave this up. I promised that I'd explain why this works. Why was it that this extremal function of a matching or a star was infinity? But I've claimed that these are the only two. Well, the answer is that all edges actually intersect in the same set. So why? Here. The answer is that all edges intersect in the same set. Well, in hypergraph land, we have a name for this. We call them sunflowers. So a little definition here. So an R uniform graph, G, is a sunflower if there is some subset of the vertices such that all edges intersect in exactly that set. So, matching, well, all edges intersect in this vertex. Here, all edges intersect in the empty set. In general, sunflowers just look like I have some core, and then a bunch of edges hanging off of that core, they don't intersect anywhere else.
Are you requiring it to equal S or just to be in S?
To equal S.
Interesting.
Yes.
That's a traditional sunflower, but
Yes. No, so yeah, we'll see actually so here we'll go. So let's make one mention and then see why this is exactly what we need. So the theorem about these guys by Erdős and Rado says that if G is an R graph with enough edges, I wrote it down, something like R factorial k minus 1 to the R. Really, there are better bounds, but all I care about is that if you have enough edges, it's true. Then G has a sunflower on at least k edges. So every graph with enough edges must have a sunflower inside of it, a very large sunflower inside of it. And this is with this traditional definition as well. And as a corollary, we get that if H is a family of R graphs, then this extremal function of H is equal to infinity if and only if H contains a sunflower as one of its elements. So in fact, sunflowers classify exactly when this function is equal to infinity. Well, this makes some sense. I mean, if I have a sunflower inside of H, I can forget about the rest of the graphs in this family and just take an arbitrarily large sunflower that has the same type as that sunflower I'm looking for. That's going to work in this way, right? On the other hand, if I don't have a sunflower, if I give you a host graph with enough edges, I can find a very, very large sunflower in it. That's going to avoid every graph in my family, and thus contradict the fact that I have to have one if I take enough edges. Yes?
2k minus 1 squared in the case that you're dealing with, right? Because R is 2.
2k minus 1. Oh, for two uniform graphs.
Yeah.
2k minus 1 squared, is that right?
So either you have a sunflower or the number of edges is bounded by...
Yep. Actually, yeah, that's a good point. Actually, this is essentially where this guy is coming from, except we don't get 2k squared. We're getting k squared, and this is tight. So yeah, you can actually improve that constant of 2 to a 1 through some other techniques for two uniforms. So yeah, this is the relationship between this and Erdős-Rada is essentially get rid of that 2, and that's the same as dealing with this one. Yeah. Segue into hypergraphs. Let's just mention a result on hypergraphs, which will also almost completely answer. Oh, crap. Of course. Of course, I break the good chalk. All right, so let's try to answer the question of hypergraphs. For that, we just need the Turan density. So let's define pi n of H. So H is a family of R graphs for whatever R you want. The Turan density of at time n, I guess, is just the extremal number versus H divided by the number of edges in k into the R, which is then choose. So just the density, this Turan graph. Now, one thing that you should notice is that this is actually a decreasing function. This can be proved simply by averaging over subgraphs. It's a pretty simple proof. So we can define pi of H to be the limit. And this is known as the Turan density of the family. This pi of H is the limit of these densities. Okay. So, theorem. If the family of graphs is non-degenerate, so this limit doesn't go to 0 like it does with bipartite graphs in the two uniform case, right? These are the non-degenerate ones. Then, ek of H is asymptotically k divided by pi of H. So it's going to grow linearly, and the constant is this pi of H.
You went not equal to 0?
Oh, oops, yes. I apologize. Otherwise, it's going to grow super linear. Yes. So this is what we saw, is that any time I gave you a bipartite graph, it was actually growing quadratically here. But, for instance, triangles did grow like this. The lower bound is simple. Just take whatever graph realizes this guy, take the clique, right, and it'll work out asymptotically. Maybe it's good to sketch a proof of the upper bound quickly. It's very simple, but I think instructive. So let's say a proof of upper bound. Well, we take G as our host graph, right? Some G. We don't know what it is. But let's say that exg with respect to H, let's say it's less than K like we want, and G has n vertices. Well, let's let T be a uniformly chosen graph on n vertices and ex of k and r, h edges. So one of these extremal graphs, but I want to just permute the vertices uniformly at random. So we're thinking about this graph T as living on the same vertex set as G. So essentially I'm just sampling the edges of G with respect to intersecting it with T. So what's going to happen? Well, if I take only the edges of G that intersect with this copy of T, it will not have a copy of H by the definition of T. But also that number of edges has to be less than K because, well, I know if I take more than K edges, I must get a copy. Right? Definition of this extremal number. But I can compute this. This is easy because we just uniformly permuted the vertices of T. This is the number of edges of G times the probability that an edge survives, which is just the Turan density here. That's just the probability of an edge of T hitting an edge of G. But now these are decreasing, so this is the number of edges of G times pi of H. And because it's not 0, we can divide across and get the upper bound. This is very simple. But it essentially answers the question for non-degenerate H's, at least asymptotic. Okay. But there are some graphs that we might want to know the answer exactly, right? I mean, sure, Erdős-Stone, so this is essentially Erdős-Stone, right? We get the answer for at least 2 uniform graphs because Erdős-Stone is a computation of pi for 2 uniform graphs. For higher uniform, okay, maybe not. But here's a question, or I'll say conjecture. Joe and I. If k is equal to the extremal number k to the r versus kt to the r, so I'm looking for a t-clique inside of an n-clique, plus 1. So in other words, if I were to pick k edges from the clique of size n, I will get a clique of size t. Then, this extremal number of kt should be exactly n choose r, and the unique extremal graph is k. I think that this feels very believable. I'm looking for a clique, and as long as I don't have a silly number, let's say, like the numbers will work out that an actual clique will work as the host graph, then that should be the right answer. I shouldn't be able to do anything else. At least feels very reasonable to me. We can prove it when r is 2. So we can prove it in the case of 2 uniform graphs. And we'll see the trick. And this trick also works for, I said earlier when we talked about this extremal function on the class of all cycles, that you can actually get around doing computations by a little trick, right, to deal with the disconnected case. And it's the same trick that will work. And will work in 2 uniform case, but not in any higher uniformity. At least I don't know how to make it work in higher uniformity. It's a trick of contractions. So if I give you, say, 2 vertices in G, so for right now we're 2 uniform land again, well, then I could look at the contracted graph, CUV of G, and this is just identify U and V. So in other words, I give you some vertices U, V. There may or may not be an edge. They have some neighbors, maybe some similar neighbors. And I'm going to contract them together into a single vertex UV, and that's just going to be connected to all of its neighbors.
Do you care what happens to multiple edges?
This is what we're going to talk about. So, what's one thing that we can notice is that if UV is not an edge, well, if I'm looking for a clique, I can only do better by contracting them. Why? Well, I haven't killed any cliques. Right? Any clique cannot use both U and V, so by contracting them together, I haven't done anything. I can only make my extremal number smaller. It's only easier to get cliques. But there's an issue. We care about the edge count with respect to the extremal number. But what if U and V had lots of common neighbors? We've deleted a lot of edges doing this. So Ryan's question of what should we do with multiple edges? Well, that's a bit of a tricky question. So what's the goal here? I should say the goal of this thing. What we're going to do is we're going to take any graph and keep contracting together vertices until I am a clique. And once I'm a clique, I know exactly how to do the extremal number, at least in 2 uniform land, which is great. But if we lose edges every time I do it, I've told you nothing about this function ek. So one thing that we could do is maybe best is just keep all the multi-edges. In fact, that's what we will do. But I don't like that with this definition. For instance, almost everything we've proved, some things we've proved are fine with if I allow multigraphs as host graphs. But for instance, our result of, say, the even cycles, I don't know how to prove that if you allow multi-edges. The proof is very specific to having a simple graph because we use Mantel's theorem over and over again. Mantel's theorem doesn't exist in multigraph land. So, instead of throwing out results, we'll do what all good mathematicians do and just invent a new symbol. We'll call it EK star. And this is the same definition, except now G can be a multigraph. Just the star means I'm allowing the host graph to have multiple edges now. I'm going to erase this. And I want to point out a few facts. In fact, the one that's important is that if H consists only of single graphs, only of simple graphs, which is everything we've dealt with so far, well, then EK of H is at most EK star of H. Right, I could only do better by allowing myself more freedom. And in fact, this will be good enough to work with cliques. The lower bound comes from a simple graph. The upper bound is good enough, and then we can milk it a bit to actually squeeze out the uniqueness. The milking is just analyzing what happens when you do these contractions and seeing, well, if I wasn't a clique to start with, I can kind of pull it back a step and get a contradiction. Conjecture. Again, if this, then they're equal. We can prove this in some situations, but in general, we haven't been able to do it. If I'm looking for a simple graph, I shouldn't be doing better by allowing my host graph to have multiple edges, because then I could just double up those edges for free. I don't know how to prove it. The best we can show is that they can't be arbitrarily far apart. Is that EK star of H is always bounded above, again, if H is a family of simple graphs, is always bounded above by EK log K of H. So in other words, if I can force a copy of H by any K edges I pick in some multigraph, I can find a simple graph on exactly that many edges, and I can still force a copy of H by only requiring a log factor extra edges. I don't know how to get rid of that log. I'd be a lot happier if it were just even a constant multiple, but I don't know how to do it. But I think this is actually a good segue into another interesting thing which can happen. Namely not only multigraphs, but what about non-uniform hypergraphs? The Turan question is kind of silly with non-uniform hypergraphs, right? I can just kind of take a Turan graph of that, a Turan graph of another, maybe match it up a bit. I don't know, but this question is actually quite interesting because I'm treating all edges the same. I still want it to be the case that if I give you any k edges, both say maybe 2 uniform and 5 uniform, I still force a copy of my graph. So some of them are simple, but I want to look at an interesting one. And I will tie it back to this in just a second. Let's look at non-uniform land quickly. And the graph I want to look at, we'll call it D for dumbbell, and it's just a single 2-edge with a loop at either end. This is a simple graph, right? I haven't duplicated any edges. All right, so let's just look at EK star of this guy. Right now, I'm going to allow you to use multigraphs. Well, if you sat down with this, I think you'd be very, very easily able to come up with a graph with at least 3 halves k edges asymptotic. Namely, just take multiple copies of the dumbbell. That'll work out with just a bit of counting. But turns out that if you take a clique of size roughly square root of k, and you put a lot of loops at every vertex, and you put a lot of multi-edges, and you throw it into linear programming land, basically this is just an optimization question about the number of vertices versus number of parallel edges at 2 edges versus parallel loops, you actually get a fairly surprising answer. Namely, that doing this construction with the right parameters, right number of parallel edges, right number of parallel loops, and about square root k vertices, asymptotically, get at least phi k edges, where phi is the golden ratio, which is roughly like 1.618. Better than 3 halves. Is this the best you can do? That would be a bit of a strange answer. Maybe it was just, this wasn't the right graph to look at. Turns out it's right. That actually with non-uniform graphs, you can actually get irrational answers asymptotically here. So, I want to give you a proof of the upper bound because, well, we discovered it after we noticed this, which we thought was very surprising, and I didn't think there was any way it was true, until the first thing I tried work to prove it. So let's again prove the upper bound. Proof of upper bound. And we're again just going to do a very simple averaging argument. So what can we do? Well, again, we have G as our host graph, right? We can assume it has only 1 uniform and 2 uniform edges, otherwise, like it has a 3 uniform edge, just throw it away, put it down any like 2 uniform or 1 uniform edge. It's not going to hurt you. So let's pick V prime from V. So pick a random subset of vertices independently, where the probability that a vertex is picked is 1 over the golden ratio. And now we're going to form a graph, G prime in G. And what we're going to do is we're going to take any loops on V prime. So any loops that on a vertex that we picked, we're going to pick those loops. And any 2-edge not completely contained in V prime. So in other words, we have our V. We've randomly selected some subset V prime. We've taken, if there is a loop in a vertex of V prime, we've taken those loops. And otherwise, we've only taken edges that hit V prime in at most 1 vertex, but no loops out here. Note that this doesn't have a dumbbell by construction, right? Dumbbell needs a loop at both ends. So we know that K has to be bigger than the expected number of edges in G prime, because G has extremal number with the dumbbell at most K. But what is this expected number? Well, the probability that I get any loop is 1 over phi times the number of loops, or E1. And the probability that I get a 2-edge is just 1 minus the probability that the edge was completely contained, which is 1 over phi squared, the number of 2 edges. Now, if you think back to your definition, at least the little phi, 1 minus 1 over phi squared is 1 over phi. And that's why the golden ratio pops out. This is times the total number of edges. We're good. It is an upper bound as well. Kind of lucky. One thing, this does generalize easily to what we call necklaces, which is where I take a single R uniform edge and put a loop in everything. This proof generalizes perfectly, and we can also modify the construction, very similar to construction work.
You get numbers different from phi, I assume.
Right, yeah, it's not phi, but it's like solutions to exactly, right, so the number you'll get is like the solution to 1 minus 1 over that to the R is equal to that. And whatever that turns out to be. But yeah, like they're defined by similar equations to phi, but they're not phi. It's powers to the R. Okay. But here's something weird. This construction, it's very important that we had multi-edges for this construction. You just took a clique and didn't duplicate it. You're not going to be able to do it, but maybe there's a better case. Turns out that EK star of the dumbbell is phi times K. But if I don't let you have multi-edges, it's 3 halves K. The construction actually requires you to have multiple edges. If I forbid you from having, actually, it doesn't actually even care about multiple 2 edges. All it cares about is multiple loops. This theorem here, we can prove it. I'm going to allow your host graph to have as many parallel 2 edges as you want, but you can have at most 1 loop per vertex. And it goes down to 3 halves. Which shows that there's something weird going on with these non-uniform graphs. Namely, maybe it's really more reasonable to treat different uniformities differently. But I don't know a super reasonable way to do that. But it does show a contradiction to our counterexample. Sorry, to our conjecture. This is a simple graph. We conjecture that you should be able to do just as well with simple graphs as you do multi-graphs, but it's false. There's a gap, constant gap between the two of them. So let me append this and uniform. If you have a counterexample, I'd love to see it. But, all right, so I'd like a bit over 5 minutes left, or whatever. Let's just, I have some other things I will say. This question is even interesting for 1 uniform hypergraphs, and we solved that case completely, but I won't go into it too much. But it is an interesting question. And there's another generalization of it, which is nice. So let's end with some questions. All right, first question. What about paths that are longer than 3? So we set a path on 3 edges. The right answer is basically a clique, right? Answer is K choose 2, and it's a clique with little pendants hanging off of it. For a general T, well, and we also know a path on 2 edges because that's a star. For general T, we can at least show it's quadratic in K. That's not hard. But we haven't been able to figure out what happens for T at least 4. But there's something very strange I want to point out. I forgot to write down the numbers. But let's again try to do our little trick of just comparing the clique and the bipartite graph. So if I look at the clique on n squared edges versus PT, this is always going to be smaller than KNN versus PT, even though PT is a bipartite graph, unless T is 4. It's a weird thing. We know both of these extremal numbers exactly. So the clique is better than the complete bipartite graph for any T except for 4 when the bipartite graph suddenly becomes better. So I think this is the most interesting case. Are the extremal graphs for the path on 4 edges bipartite? I don't know how to prove it. But this suggests that it's more likely than cliques. Again, not a proof, but just reasoning. 2. What about cycles on 4 vertices? 4. We weren't able to get this answer, not even up to a constant, unfortunately. The best lower bound we can prove is a constant times k to the 4/3. And the best upper bound is a constant times k to the 3 halves. Conjecture, this is correct. So this is the answer that you get from just taking a clique as the host graph. And this upper bound is actually done very similarly to randomly intersecting the polarity graph with whatever host graph I give you. But the number of vertices kind of throws you off. Like, if you could show that any like really good host graph here has at most k to the 2/3 edges, sorry, k to the 2/3 vertices, then that improves the upper bound to k to the 4/3. And that's not true in general, but maybe there's some way to milk that fact. The proof of the upper bound is very simple. Although I have 2 proofs of it. The other one doesn't. And I guess last thing to mention is, why did we optimize edges? We were asking, what host graph is best for, some given family. Maybe edges wasn't the right answer. It's just what we liked. So what we could have defined is if I had P being any increasing graph parameter, we could have just as easily defined, let's call it E sub pk, to be the max value of P, such that the extremal number is again bounded. Oh, sorry, of H. You can decide whether or not you want to use multigraphs or not. I don't care. But we could have defined this for any parameter P. Some parameters are stupid. I think that maximizing vertex count is pretty silly, personally. But one I do think is interesting is when you take P to be the chromatic number. Well, in this case, E chi k of a matching or a star are no longer trivial. And I don't know the answer to them. One thing that's easy to see is that this parameter can never be infinity. That's not too hard to show. But even a matching or a star actually becomes somewhat difficult with this parameter. The only thing I can show is that if the chromatic number of H is at least 3, then E chi k, so the graph with the largest chromatic number, which avoid such that any k edges forces a copy of H, this is asymptotically, let's see here, I wrote it down, 2 plus 2 over chi of H minus 2 times k, so k in the square. So I can show that, but again, this only works when you're not bipartite. This degeneracy really kicks in again. If your chromatic number is 2, it must grow super square rootedly. You say that word. Is there a term for that? It must grow super square rootedly. There we go. Must grow faster than square root of k. Yeah, so there are lots of questions you could ask here. Another one that I think is interesting is, what's the right way to deal with non-uniform hypergraphs? Maybe different weights. You could also artificially introduce different types of edges into 2 uniform graphs by, say, coloring them different colors and forcing what you find to be actually a colored copy of your graph. Lots of different questions here, but thanks for listening.
Let's sing the